Okay, so tell me what your schedule is in the next couple of weeks. Lindsay responded to my suggestion about talks that we wait until next week, so you have the weekend to make your PowerPoints. I'm seeing one shaking head.
Yeah, I agree with Lindsay. I mean, that will give us this weekend to work on our presentation.
Okay.
And
But that means 7 talks. And so the question is when can we do those? Because Tuesday, we're only scheduled from 10 to 12. Maybe we can, get 3 talks in that block, but we're certainly not going to get 7 in.
yeah.
We could go Monday morning, Tuesday, you tell me, what else do you have next week?
I am
Wednesday class just ended, our Wednesday morning class.
Yeah.
So
Most of us should have that block open.
And how about Dr. Hostler? Are you still meeting with him Thursday?
Yeah, from 10 to 12.
Right. So we have Tuesday morning, we have Wednesday morning.
And we have Monday morning too.
So is everybody okay starting Monday morning at 10 and do Tuesday at 10 and Wednesday at 10 until we finish?
That's fine with me.
Yeah.
Sounds like a good plan.
Anybody else?
That's fine for me.
Okay. So then I'll just need people to start volunteering for Monday, Tuesday, Wednesday. If nobody
I
sort of
can still go first.
say again.
I can still go first.
Okay, I'm sorry. Who is that?
Sarah.
Sarah. Okay, I was guessing, but I wasn't sure. Okay, so Sarah is going to go first on Monday at 10.
I can go after. I can stick with the number 2 spot, Dr. Correa, and go second.
Okay, so we got 2 on Monday, and then we'll need more on Tuesday and Wednesday. So let's leave it at that for the moment. Thank you. Okay.
Yeah.
Hold on a second. I just want to look at something. So Sarah, you're presenting the Ernesto Freire paper. And Lindsay is presenting the Van Holt paper on sedimentation of DNA fragments. Okay. All right, good. Okay, so where am I? So the 8th assignment, which is sort of, I think, where we are, because we were discussing 7 last time.
Yeah.
Most of these, the first couple of questions really are just applying the equation for absorbance. Let's make this bigger. Okay, so the first one is basically, if I give you an extinction coefficient and I give you a concentration in a 1 millimeter cell, what is the absorbance? And then what is the percent transmission? So this is really about sort of the equation and just applying the extinction coefficient, which is 6,000 for this base, times a path length of 0.01 times a concentration. And when you plug in the concentration, you'll get something like 0.06. And then to get to the transmittance, you have to take the inverse of this basically, because absorbance is the log of I0 over I. The inverse of that is raising 0.06 to the power of 10. And then inverting it, because transmittance is not I over I0 over I, it's I over I0. Okay, and so you'll get something like 87% in the first part and 25% in the second part. The second one is asking what the concentration is if you have an extinction of 16, a path length of 0.5, and absorbance of 0.73. And again, you set up a simple equation and then you solve for C. Okay, so it's pretty straightforward. The third one is if you had a mixture and the mixture was two components, distinguishable but overlapping absorption spectra. So that could be any number of things. It works a little better with DNA because the bases all have slightly different extinctions. If you go back and you look at the spectra from the chapter, you can see that the bases are slightly different peaks. So the thing is that you sort of have to have, you have two unknowns. You have concentration of one and concentration of the other. Okay, so to solve for two unknowns, you need two equations. So, so the way that in my way of doing this, you have an absorbance at one wavelength and an absorbance at a second wavelength. And then you set up two simultaneous equations. The first component at the first wavelength gives a certain signal. You have to know the extinction at both wavelengths for both components. Okay. And so you have two equations, two unknowns. That's quote unquote algebraically solvable. Solve for C1 in the top equation, and then plug that into the lower equation, and then everything will be in terms of C2, and you can solve for C2. And then once you have C2, you can go back and solve for C1. This is the ideal situation where you need to know something about linear algebra and matrix to solve this, but that's basically the way you have to solve this. If you try eliminating other stuff, somebody tried eliminating L, you still have two unknowns. You can try ratios, but I think you still have two unknowns in that setup. I may not be right about that, Ahmed, but I think that's right. But this, I think, is the way that I would solve the problem, certainly, that I would set up two simultaneous equations, etc. The way that this is solved more universally is more complicated than that, but it's the same thing. Except it's not done with two unknowns, it's done with 100 unknowns. If you have, can I get this to work here? Yeah, there we go. Pen. So if you have two spectra, and this is going to be absorbance. If you have two spectra of two proteins, basically their spectra will, for all cases, will sort of look like this, but maybe the second one doesn't look quite that way. Maybe it looks a little different. I'm exaggerating a little bit. They basically have a peak near 280, 276. 280 is sort of the peak of tyrosine, of tryptophan, excuse me, tryptophan, and 276 is sort of the peak of tyrosine. So it depends on the tryptophan tyrosine ratio. The other thing that contributes are disulfides. It doesn't contribute as much. We went over that in one of the papers that we mentioned in terms of predicting extinction coefficients. It tends to have a peak somewhere in the 260 region, I think. I can't remember what that wavelength is, but it's much smaller. And what the modern method would be, and we use this actually in multi-wavelength analysis and sedimentation experiments, but it would work with anything, is not to collect two absorbance, it's to collect as many as possible. And across this sort of scan, if this goes to out here, we're at 290, and here we're at around 255, and etc. So if we were to collect, I said 90 there, so 80, 70, 60, 50. So if we were collecting 40 wavelengths across this span, then you would literally set up a matrix problem where you have 40 wavelengths worth of data for, so you would have wavelength in one column, and then you would have absorbance in a second column. But then this would be compared with the absorbance of component 1 and the absorbance of component 2. And these would be the spectra that we know are true at some concentration for these two unknowns. Okay, so I'm doing this with protein, not with DNA, but you could do it with DNA as well. And so this becomes the same thing. You have an absorbance at multiple wavelengths, and they're equal to some linear combination of column 3 and column 4. And so each position is basically a wavelength this way. And so this becomes a matrix problem where you have absorbances equal to these sums, but it's at multiple wavelengths. And then so when you set up the matrices to solve this problem, this is what you get, okay? And so it's not two unknowns, it's 40 or 60 or 80, however many you collect unknowns. And so there's long combinations, and then there's a matrix solution to this, all right? And so this is the way you would, state of the art, solve this problem, okay? 2 is gonna work, but it would be better if you had 20 or 40 or 60. And so in a normal spectrophotometer, you just collect all of them. The problem is you need to know the extinction coefficient at every single wavelength, okay, all the way down. So you have to collect data and have a sort of a table, a lookup table of all of the extinction coefficients, and then that would allow you to solve for the concentration. And notice, every one of these mixtures involves a matrix or a row, basically, of values. And so you still know there's only 2 components with 2 unknowns. In principle, you could do this with 3 components or 4 components, but you need enough equations to do that. Okay, so if you're going to solve for 3, you got to have at least 3 wavelengths. 4, you got to have 4 wavelengths. It begins to become a little bit too big a matrix. The matrix gets really big. Once you get past, certainly past 10, but even once you get past 5 or 6, it becomes difficult to solve that. But nonetheless, you can do it, and you can solve this problem this way. Okay, and so we actually have written the code for that in the SetAnal program that I showed you briefly one day. Okay, for multi-wavelength analysis. Okay, but this is sort of the minimum solution to the problem. Any comments or questions? Two equations, 2 unknowns. Okay. The CD questions in chapter 10, I think it was, are expecting you to sort of be able to know something about here. So this one is expecting you to sort of know something about the CD spectra of proteins. The beta turn has a minimum around here. So it has a minima around 215 and has a maxima around 290 or 190 something. And then an alpha helix has a 208, 222 with a maxima somewhere down around 190 something. 195, 196 is where this peak is, if you can collect data down there. And so that's sort of what the problem is doing. It's defining in aqueous buffer a protein that has a minimum at 215 and a maxima around 196. And then you put it into ethanol, you put it into alcohol, And suddenly you end up with a 208, 220 minima, which implies alpha helix. And then there's an increase in the signal at 192 over the 196 value. And that's what you expect if you go back and look at what I just showed you. That's what you expect for an alpha helix. It moves a little bit deeper, so it's 192 instead of 196. Okay. And so the description is 100% beta sheet going to 100% alpha helix. Alcohol will do this to proteins. Ethanol, methanol, there's a lot of different alcohols that are used to sort of induce converting a protein into an alpha helical structure. It's not unusual for a protein to be 100% beta sheet. Beta lactoglobulin is one of those proteins, but most proteins have a mixture. And so this could have been a much more complicated problem if it was. So imagine this protein is actually 20%, 30% beta sheet and another 40% alpha helix, and then it gets converted all to alpha helix. It would be a little less easy to figure it out descriptively. Comments? Questions? So this nucleosome problem, sorry, I've got these on different pages. They won't, well, I can't do it from here. Can I do it? It gives you temperature data. And as you melt, the absorbance changes at 260. So that means that implies that something is happening to the DNA. And then the CD spectra changes. And what's interesting about this problem is that there's both a protein and a DNA. And so the hypochromicity is changing as things melt. And you can see this melting process happening at a fairly low temperature, actually. And then the DNA is the protein is also undergoing some kind of a melt, although it happens at a higher temperature. That's part of the question. So somebody want to tell me what they did for this? So I don't always do all the talking here. And what the logic is? You sort of have to know that when DNA melts, something happens. What happens when DNA melts?
It becomes single-stranded from the double-stranded, and it absorbs more light.
Okay, so its absorption goes up. So when
Yeah,
you make double-stranded DNA, it suppresses the absorbance.
yeah,
And when it melts, you get hyperchromicity, and so you get a gain in absorbance.
absorbance. Yeah.
Okay, and so that seems to happen here around 50 degrees. That's when it starts. And that sort of coincides with a similar sort of thing starting to happen in the CD. And then what happens? What else?
And then it stops. I should know a way.
So what happens to the CD spectra? Do I have that open here? Oh, here. That's a protein. So this is CD spectra. Curve A is, and C is a monomer. So is that making sense as well? What's happening there? See, so the CD spectra, the monomer has a small CD spectra. Monomer is C. Let's let me write here. The monomer is C, so it has a small spectra. And then the polymer, a dimer, it begins to gain a spectra, but the polymer, which is A, has a huge CD spectra, and it's saying it around 270 or so. So it's this increase that is observed going from cold to warm. And so that seems to be what's happening in the DNA.
Yeah.
And so that's why the peak around 270, which corresponds to all the bases in the DNA, not just a particular base, increases dramatically as it goes from 20 degrees here to 85 degrees. So that's consistent also with the DNA melting. Yeah. The protein has a deep minima. And so again, if we go back and we look at the protein, oh, is that right? No, that's not the right one. This one. As the protein melts, it loses its, I don't remember if that there was a melting. Yeah. So you can see random coil here. So if you started out with some kind of a signal, some minima, and the minima it was giving us is at 223. So that's sort of a marker for beta, for alpha helix. And then it goes up, it becomes more positive, okay? It loses its negative signal and it becomes more positive. Okay, and so that's what's happening here. It's getting smaller at 223. So the DNA is melting, gaining absorbance, hyperchromicity, but it's also gaining absorbance. And that's specific for the DNA. And then the 223 is specific for the protein. It's going from some structure, which we might assume is, because it's a 223, it sort of is a marker, if you will, for alpha helix. And then it becomes more random coil-like, and so it gains a signal. Okay. Okay, so that's basically what's happening in this particular observation. So I know you're not going to know the answer to this. This is the structure of a nucleosome, right? Because the way the question begins, nucleosomes, all right? It's about 150 bases of DNA wrapped around a protein core. It's a histone core. Tell me what you know about histones. What's the histone core?
Yeah, that was my question, Dr. Correa. So it's made up of what, is 8 subunits or something like that?
Right, it's 8 subunits.
So
in the DNA,
yeah, that's
go ahead.
about the loss of quaternary structure of the histone as the DNA melts and unwinds around it. That's how that affected the spectrum.
Right. Okay. And I have no idea who teaches this to you. Probably does David teach this to you? Does Michael teach? Who teaches this to you?
Pass.
Dr. Brown.
Dr. Brown. Right. Okay. So David works on histones, although he doesn't work on core histones.
He works on linker.
He works on the linkers. So DNA is it's a core with DNA wrapped around it, right? And then there's another core with DNA wrapped around it. Okay, there's my bad art. Okay, so the histone core, the H1s, are sort of at this interface here where it attaches to the cores, right? Something like that.
Yeah.
Okay. And so
H2.
Who solved this problem? Do you know? Does David teach that? When was this problem solved and who solved it? Remember, I keep saying things to you. Everything in books comes from some paper. Okay, it's not just somebody suddenly sat down and wrote a textbook.
Yeah.
Although somebody did sit down and write a textbook on chromatin.
Yeah.
Who wrote the textbook on chromatin? Anybody know?
He might have told us, but I don't remember as of now.
Wikipedia says that the nucleosome was solved by the Richmond group.
Okay, so that's probably a crystal structure.
Okay.
Okay, so that's not wrong. That's correct.
First thing I could come up with.
That's all right. That's all right. People tell you don't use Wikipedia, but I find Wikipedia really helpful.
Let's see. Roger Kornberg figured out the length of DNA wrapped around it. That was just by microscopy, though, or estimated by microscopy.
Yep. I'm looking for my copy of chromatin and I cannot find it. My goodness, I have too many books. Well, I'll get it eventually. So the textbook called chromatin, it actually didn't get published until the late 80s, I think. Was written by Ken Van Holt.
Oh.
Okay, all of the lecture material that I'm giving you in the second part of this class is from Ken Van Holt. And one of the reasons that a lot of his questions involved DNA and chromatin was that Ken worked on chromatin for many, many years. He actually started working on polymers, and then he switched to he did a lot of work on hemocyanins, so oxygen binding proteins, and he was doing that work when he went to Oregon initially. But then in the early 70s, he actually started working on DNA and chromatin, and he is actually one of the people who initially proposed what the structure of nucleosomes are. And it's described in the electrophoresis chapter that I didn't actually cover all of that material because it describes dichroism and the orientation of the DNA and the protein. Because the early models had protein on the outside and DNA on the inside. And it was Ken Van Holt who came up with the original model for chromatin in the 70s. And then he started writing a textbook on it. So he had already written this textbook, the early versions of this textbook. Well, I have no idea why I can't find my textbook, my version of this. It's here somewhere, I know it is. But he's the one who actually solved this, and he solved it by electrophoretic methods. Okay, so people in his lab, okay, and so that's the early solution to the problem. Okay, so where are we? We're at 10:30. So do we have any other questions about that particular problem?
No.
Okay, and so it was a combination of, so the hyperchromicity and the change in the CD and both the protein and the DNA were part of the solution to the problem. And this is one of the reasons that these sorts of techniques are very powerful, because they are informative about the assembly state, single-stranded, double-stranded, of the DNA and the denaturation of the protein. Okay. So where are some of you guys with these later problem sets? Some people have turned them in and a lot of people have not. So 517 is an interesting combination of sedimentation and electrophoresis. So they give us an S value and they give us a diffusion coefficient. And they give you a V bar so you can calculate a buoyancy term. And then they describe electrophoresis. And they run it out in the presence of beta mercaptoethanol, and they get two fast-moving bands. And then they run it in the absence of beta mercaptoethanol, and they get a fast-moving band and a slow-moving band. And then they give you a set of standards. So what do you do with the standards? What do you do with the sedimentation and diffusion? Let's start with that. What do you do with sedimentation and diffusion?
Find the molecular weight of the
And what do you use for that?
electrophoresis.
Huh?
What was the question?
So how do you get the molecular weight?
From the sedimentation and diffusion coefficient.
Oh, that's correct. And can you give me more detail? What formula do you use?
I've got this written in my notebook. So it's S over D, sedimentation coefficient over diffusion coefficient is equal to molecular weight times 1 minus velocity.
V bar, it's V
V bar.
bar, not velocity. That's
Oh yeah, V bar.
partial specific volume.
Yeah.
Divide
Times RT, R and temperature.
Right. So remember in the derivation, we actually started with over NF, and diffusion coefficient is RT over NF. So if you divide one by the other, you get this equation. The NFs cancel, so there's a shape factor, and you get this equation. So given S, given D, given the V bar, they give you the temperature, you can solve for M. Okay, so you get a molecular weight. And I think if you plug all the numbers in here, you get something around 66 kilodaltons. Okay, you get something like 66,000. Yes?
Yes.
And then you do electrophoresis and you get two fast moving bands. So notice in the electrophoretic pattern, 10 centimeters is somewhere down here. Okay, so this is telling you that you're getting something in this molecular weight range that's sort of small. But then when you don't have the beta mercaptoethanol, you get a band around 5.6, which is somewhere around here. So you're getting something in the 30,000 molecular weight, approximately, and you're getting something in the teens, 16,000. Okay. And so you're getting two bands, but they have to add up to 66,000. And that's sort of the trick here, right? The sum has to be 66,000. All right. And so for this to add up to 66,000, then you have to figure out what the stoichiometry is. So this is a combination of stoichiometry and sum of the molecular weight. Okay. So maybe you need two of these. And these added to that will give you 66,000. Okay. So I'm approximating the numbers here. Okay, so what's the plot that you plot to get to get these numbers out of the distance moved? I don't think I have the electrophoresis chapter opened up. Where is It's the electrophoresis chapter. There's that dichroism stuff I mentioned that helped solve, that may not be where it was. It's this one. Where did we talk about that? Sedimentation, electrophoresis may be at the back of this chapter. Sorry, I'm now being distracted by the, there's the sedimentation coefficient equation. Well, I'm not finding it. No, here we go. This is where it was. No, that wasn't it either. Okay. Oh, there it is. This is dividing one by the other. That's the answer to that question I asked a few moments ago. So this is a question 534. Let's keep moving here. Where's the damn electrophoresis? Equilibrium, sorry. Electrophoresis, there we go. All right. That was the Ferguson plots. And here is the logarithm of the base pairs. So this is basically molecular weight versus the distance. Okay. And so you'll get a straight line if you plot the distance migrated versus the logarithm of the molecular weight, or something proportional to the logarithm of the molecular weight. Okay, and so if you plot log of molecular weight on the x-axis down here, and the distance migrated, you'll get a straight line. And then from the band position this way, you can guess a molecular weight. And that's how this is done with proteins, and this is done with nucleic acids this way. Okay. We now buy kits that have standards in them. So you buy what are referred to as low and high molecular weight standard. So this would be a low molecular weight combination. The high molecular weight combination would have, it would probably have myosin, and I can't remember what there's some other higher molecular weight that extends up into the 200,000 molecular weight. It would not have lysozyme or alpha-lactobumin. I don't actually ever see that one in the standard. It's usually something like lysozyme at the low end. Okay. So let's talk about this. 2 pieces of DNA. This may be too much detail, kind of a question. You've got to know what equation 548 is, which might be, it's not that one. Might be this one, 548. Is that here? $551, there it is, 550, 548. So it's the charge over the shape. So the mobility is charge over shape. The charge on a given free electron. So from the pieces of DNA, I think that question had 400 and 800. And then there's some shape factor that you have to solve for. Okay, and is it 400 and 800 is the way that that's expressed? 400 base pairs long, 800 base pairs long. So if it's 400 base pairs, is that actually 800 charges? And if it's 800, is that actually 1600 charges? Charge is proportional to length. So maybe that's not an issue here. It has a 25 angstrom. So where are you getting the shape from in that problem? What are you using for shape? It's
So
a rod.
it's a rod, yeah. It's a rigid rod.
It's a rod. And so where do you get that? Is that in this part of the lecture, or is it
Yeah.
somewhere?
It should be in one of the table. You have to check it.
It's the bent DNA topic. Where did we do that? That's proteins. So what do we use as an equation for shape? I don't think it's actually in that chapter. Where is it coming from?
If you look at the lecture 13, slide 17, it gives you the equation to find the frictional coefficient. F by F naught, that's the formula that I use for the rod to find the F, frictional coefficient.
Lecture 13.
Yeah, lecture 13, slide 17.
Not actually sure where I have that. What day, where was that? That was not part of 5 and 6, was it? No.
You can open it from Canvas as well.
Oh. Is it in Canvas? Okay, let's go to Canvas.
Yeah.
Let's go to Canvas.
And then the diffusion and sedimentation, yeah. And then, yeah, the second,
Oh, this one.
yeah.
Aha.
I think you have to download it. It showed me this last time. I just wanted to open it from there.
Okay. I have to download it, even though
Yeah. Slide 17.
Okay, so rods have a frictional coefficient with this formula. So this involves this weird Perrin parameter.
Yeah.
And you basically have to solve for the ratio of the half length over the half diameter.
Yeah.
Okay, and so, and then you plug that p-value in to this formula, and that will give you the F over F naught. And then you can use F in the electrophoretic ratio that we just had open. So that was also in here, wasn't it? Yeah, so you get F that way, where P ends up being in that formula, P ends up being something involving, I think it's
Alpha.
over beta, but that's basically the length over the diameter.
Mm.
Okay, or the half length over the half diameter or something like that. And that's where you get, that gets plugged into that equation, which then gives you F, and Z comes from the charge because you know how many charges you have for double-stranded DNA. And then this is asking you for the ratio of those numbers. Is that right?
Yeah.
Okay. This one is another one of these calibrations where, let me read something here. A digestion is electrophoresis to a lane of restriction fragments of a bacteria of known size, migrates on the gel. A nuclease at the junctions between nucleosomes to make a series of oligonucleosomes to determine the DNA repeat size. And so someplace up above, I just wrote out what the structure would look like. I don't know where I did that. Oh, there. So if it's going to cleave at junctions, basically it's going to cleave. Oh, come on. Give me the pen. It's going to cleave at junctions. Okay, it would break it up into pieces. And so you would end up with pieces this long, or maybe that long, or maybe that long if it's not completely digested. And so I think that's really what these data is showing. If it was completely digested, then all of the pieces would be this long. And it would include the piece that wraps around the nucleosome. Okay, but instead, I think it's partial digestion. So they're getting some kind of a mixture of digestion fragments, right? And again, this was in fact the way that this problem was solved. And a number of people were involved in this sort of problem. I don't think this wasn't Ken. I think Lindsay was reading off that it was some other people who were doing this. But you are now taught that it's 200 base pairs. It's 200 base pairs between nucleosome, but these fragments, if you solve using this calibration data set, you will get, I think, something between 200 approximately and 400 and 600 and 800 base pairs. Yes. And so that will tell you how long each fragment is. Yeah. And so that's basically it's not really a trick. And so this is, again, an example of Ken was involved in nucleosome molecular biology, biochemistry, and that's why he was interested in this. The paper that Lindsay's going to cover on the length of the S values, basically the shape factors and the S values of DNA fragments, is part of what they were involved in, trying to isolate different fragments of DNA and conclude something, knowing, for example, S values or knowing migration on a gel. Do we have any comments or questions about this? Okay, so I know that some of you maybe had something coming up at 11 or had another thing happening in the next hour. So tomorrow we're going to talk about thermodynamics of drug binding, and we're going to talk about the origin of things like the enthalpy and the entropy in terms of drug binding. So it's more dissecting of or parsing the contribution to the enthalpy and the entropy. The paper that Sarah's talking about actually discusses more of that as well. So it's meant to be extra discussion of the problem. So I'm going to now make one final request, and then we'll break until tomorrow. So this was a new format for me teaching, only in the sense that, because I've covered most of these topics in the past, although sometimes I've completely changed books and done a different combination of things. But certainly in the 80s and 90s, this is the way I taught. And then on and off in the 2000s, this is the way I've taught. Certainly in the last 3 or 4 sessions, 3 or 4 years that I taught. But this was different because everything was online. And this was different because everything involved these PowerPoints that I was throwing together. Okay. And it seems to me, I may be wrong about this, that because of the way I taught this year, maybe I went too fast because I had PowerPoints. Although I don't think I went faster than I used to, but maybe I did. And maybe I covered a lot more information. And maybe I gave out a lot more problem sets, although 8 or 9 or 10 is the typical number, I think, that I usually ask. So you don't have to answer me right now, and you don't have to answer me when everybody else is online. But what I want you to do is, I think somebody is going to send you an evaluation form anyway for this class. Maybe you've already gotten it. I have no idea. They usually show it to me in like 6 months. I never usually see it until well after the fact because of how well organized somebody is somewhere. But what I'm saying to you is that the evaluation that you get is not really what I'm looking for. What I'm looking for is your feedback to me. You're not obligated to do this. What helped and what didn't help, what worked and what didn't work. Was it too fast? Was it too much detail? Was it, my opinion, of course, is there's no such thing as too much detail. But some feedback about what it is, and I'm talking to that worked or did not work for you. Okay. My opinion about this teaching, not just a course, but sort of graduate education in general. I feel the same way about undergraduate education. It's our job to sort of challenge you and to make you aware of what the bar is, where the level of information is for you to succeed at this. And so I don't think that there's a limit. I expect people to sort of rise to the occasion, if you will, or at least recognize what the standard is. But you don't necessarily have to agree with me. I'm just the crotchety old professor who's demanding perfection out of myself and you. But I need you to give me your honest evaluation of how this did or didn't help you, and what might have been what might have been better. I don't think the face-to-face necessarily would have been better per se, but I think the PowerPoints and combining the PowerPoints, then if and when I teach this in 2 years, the PowerPoints will now get edited and modified in some way. So it will be easier in that regard, but then they'll be edited in a way that maybe anticipates a lot of the problems that come up, a lot of the challenges that come up. So it'll be helpful in that way.
Dr. Correa, I'll chime in on here and say that I think the format was perfectly fine. I think the pace was fine. I think there's one confounding factor this semester, which is that we were as a class taking that bioinformatics class as well as the enzymes course, and I don't think that's happened before, and it was a major time sink. So I think that has impacted everything.
Yeah, yeah,
But these problem sessions, that help sessions, extra weekly meetings, that's helped tremendously.
right. Yeah, and certainly in the 90s, I think I did a lot more problem sessions earlier on in the course, and that probably is what I should have started doing really early on. So is the bioinformatics just once a week?
It is, we finished it, we turned in the final on Friday, but it was a 3-hour block on Wednesdays with a pretty lengthy homework every week that was due the following Monday. And it was just, for me anyway, it was just a big time sink. It was a 12 or 14 hours a week, sometimes extra assignment.
Yeah. And that was primarily taught by one person or multiple people?
By two, it was Drs. Ashley Robinson and Eric Ballander.
Okay. And it was mostly teaching you how to use software and apply software packages?
Pretty much. The second half of it was mostly software packages or libraries for R. So we had to, it was almost all of it was command line. We worked directly in Unix for the DNA side of the half of the class. And then we worked in R for the RNA-seq side of the class. But it was learning which software packages were available and how to utilize them to process sequence data.
Ah, so you had to learn Unix and R to do that.
Yes. Some of it anyway.
Mm-hmm. Huh. Well, I've never taught this with coding, and I keep saying that I should. My friends who teach it that way use Python, or they use Mathematica. So that would have been a third or a fourth language. Okay. Any other comments, you can just email me. Okay. All right. I'll see you tomorrow. All right.
Thank you, Dr. Correa.
Thank you, Dr. Correa.